Hi there. I will be conducting a full series of videos on the subject of multivariable calculus. This is the first introductory video in that series. It's just going to focus on introducing functions of several variables. Thus far, in your study of calculus, many people would have been introduced to just studying functions of one variable. That is, y would be a function of x. Y is the dependent variable and x is the independent variable. We would have some quantity or some phenomena y that would just be dependent on one single thing. An example of this could be perhaps the growth of a tree. We could have a tree that's 1 year old and has a particular size. We could have another tree that's 5 years old and it could be substantially bigger because it's older. So what we're saying is that the height of the tree or the size of the tree just depends on the age of the tree. We could write h as just being a function of t. But in the real world, it's rare that we would have or we would find quantities of phenomena that just depend on one single thing. If we think about the complex world around us, we can easily see that we have to think of many factors. An illustration of this would be, of course, the weather. If we were to determine the amount of rain that is going to occur on any given day, what would we have to think of? Well, we may have to consider the air temperature. We could perhaps even think of the air pressure, the humidity in the air, that is the amount of water vapor in the air. We could also probably think about maybe the wind speed. We could think of the geography of the land. We could think of the ocean currents. There's probably a million different types of variables that we could consider in trying to predict the amount of rain that is going to happen in any given day. There's hundreds of variables, and some of these variables may even depend on each other. Even with this example of the tree that we considered earlier, we did reduce this to one single variable by making a number of factors to remain the same. For example, maybe the type of tree, the species of the tree, maybe the area in which it was planted, the amount of minerals in the soil, maybe the amount of water that both trees were given. So we kept all of those constant and just only considered the age of the tree. So in other words, we considered that the tree was the same type, it was in the same place, etc. So how do we now extend our knowledge of calculus to consider more than one variable? So calculus has been focused on considering how does, for example, the height of the tree change with time. So we now need to extend that thinking into more than one variable. And the easiest way to do it would just be to consider, instead of one variable, two variables. We would create a new variable or a new dependent variable z that's now dependent on two independent variables, x and y. A simple illustration of this that you would have seen is the area of a rectangle. The area of the rectangle depends on the length and the breadth. So what we could do is just create a variable z, and it is the product of the length, which we can call x, and the breadth y. So we have z is equal to xy. This is now a function of two independent variables. So the question now is, how do we draw this? How do we think about it? How do we plot it? What does it look like? And that sort of thing. Because when we had one independent variable, we just had a two-dimensional graph. We plotted y and x, and maybe there would be some curves that we could consider, a linear curve or a quadratic curve, etc. So what does three variables look like? That is one dependent and two independent variables. So these z values, they are a vector of values. They can go from minus infinity to infinity. In this example, we're considering the area. So the area has to be greater than 0. So the starting point would be 0, 1, 2, 3, etc. And now on the right-hand side, we have xy. So what does xy mean? Well, we're now considering a matrix of values. the rows of this matrix would be the x values and the columns would be the y values. So in the first row, we could have x equal to 0, y equal to 0, then x equal to 0, y equal to 1, x equal to 0, y equal to 2, and so on. And in the second column, we could have x equal to 1, y equal to 0, x equal to 1, y equal to 1, x equal to 1, y equal to 2, and it will carry on like that. So if we were to draw this graph, what's going to happen is that it's going to be a 3D plot. So it would be an object, it would be a shape. And it's difficult to draw these kinds of diagrams, do these kind of plots. So there are software that people would normally go to, and you could just do a simple search for it, and it would come up. You would just put in your equation, z is equal to xy, and then you would have an idea of what it would look like. And in this instance here, it looks something like this, where we have our z values, which we can see on the left-hand side, and we have our base consisting of x and y. So that would be this matrix of values here forming the base, and then the third axis coming out of the page is the z-axis. Another example in which we could think about, in that we could try to actually draw, is the function maybe z is equal to x squared plus y squared. What does this function represent? What would it look like in terms of a 3D plot? One technique or one strategy that can be employed into trying to plot a 3D graph like this is to consider the various planes. So if we were to draw these axes, we would have a third axis, the z-axis. We could have a y-axis, and we would of course have the x-axis. So the strategy is to think about what would this plot look like in the various planes and plot the graph based upon what it would look like in the various planes. So when we speak about the xz plane, we're speaking about the plane that runs something like that. If we speak about the xy plane, or the zy plane, we're talking about the plane that runs like that. So if we were to put these different variables to 0, that is x and y, and try and figure out what it looks like in the various planes, we might be able to plot it. So if we set x equal to 0, then we get z is equal to y squared, and this is just a two-dimensional graph, and it's a parabola, and of course it looks something like that. And if we do the same with x, that is set y is equal to 0, we're left with z is equal to x squared. That's z and that's y. And now if we plot z and x, we are left with the same thing. So what we're saying is that on the zx plane, the graph looks something like that, and then it continues on into 3 dimensions. And on the zy plane, it also looks something like the parabola. So if we were to complete this graph, we would draw a circle like that, and that would be what this graph would look like. It kind of looks like a champagne glass. And if we put this plot in our software that we can run online, then we see that it looks something like this, which is kind of what we had come up with this as well. So another important point that we can use to conclude this video is we can now cut this graph in different planes. We could cut it there, we could cut it there, and we could cut it at each of these different points. That is, if we look at it from the top and we were to cut out chunks of it in the manner in which I've drawn it, what would it look like? If we draw, that is the projection on the xy plane, that is, we're drawing the base xy, and we're looking at it at the top, what are we seeing? At the point of origin, we're just seeing a dot, okay? And then as we go up the z-axis, we're seeing different values of z in which circles appear. If we look at it at the top, we just see a circle, and if we cut it off at different points, we will see smaller circles until it's 0 at the origin. So we see a series of concentric circles if we were to look at it at the top. So what these are called are level curves. So these play an important role in the topics that we will consider in previous videos, or sorry, in the upcoming videos. So to summarize this video thus far, what we have considered is functions of multiple variables. We saw that calculus simply depends on one variable at the start in which we study it. We see that the world consists of many variables. We now have to extend our study to more than one variable. So we consider two variables. We create a new dependent variable z, which is dependent on x and y, which are the new independent variables. We see that our base is the x and y axis, which is a matrix of values, and we get a single output z. And thereafter, if we were to try and plot different values or functions of multiple variables, we can consider different planes, what it would look like in different planes, and then try and figure out what it would look like in 3 dimensions. And we can verify this by using online software to get an indication. We can then look at the projection of the graph at different values of z on the xy plane. And in the example that we considered, z is equal to x squared plus y squared, we see that we see a series of concentric curves. These are called level curves. So thank you for watching, and in the next lecture we will consider derivatives of multiple variables.